Hi, Bob Young back at you here, and in this instructional video we're going to continue looking at some exponential models and curve fitting. Now, the number e, which we talked about in our last exciting episode, is important as the base of an exponential function for many real-world applications. For example, in situations involving growth or decay of a quantity, the amount or number present at time t often can be closely modeled by the function below here. Y equals y sub naught e raised to the kt power, where y sub naught is the amount or number present at time t equals 0, and k is some constant number. Now, usually what they do in these type of problems here, y sub naught is what they call the initial amount. Okay, so we're going to go ahead, and I'll just abbreviate amount here. And when this k number, the constant number at time t equals 0 is positive, we tend to have this increasing exponential look, or they call it growth sometimes. They'll call it sometimes growth problems because that's a positive number. Now, when k is a negative number, then you'll have something, the function will go like that, and then you'll have what's called, it'll decrease or decay quantity. So the k number, the constant, is very important here. So what we're going to do is we're going to look at some data here. Now it says if current trends of burning fossil fuels and deforestation continue, if we keep cutting the trees down, then future amounts of atmospheric carbon dioxide in parts per million, ppm, will increase as shown in this table. So notice they start with the year 1990, how much carbon dioxide was in our atmosphere, and we've been measuring this, 353 parts per million. 2000 it increased, 2075, and look where it's heading if we keep going here in the year 2275, 2000 parts per million here, and we know that, leads to global warming and so forth, so hopefully we can get that under control. So what we're going to do is we're going to make a little scatter diagram here. So those of you that's, heading towards statistics may be seeing something like this. And it says, do the carbon dioxide levels appear to grow exponentially? Now notice here, the x-axis down here, it looks like they've got parts per million, starting with, about 300. So we used a graphing calculator. Now I know not everyone has one, and they set the x-axis from 300 to 2,300. And then y, they went ahead and put the years over here from 1975 to 2100. All right, now it certainly does look like if we were to connect the dots on this data here, this thing would be growing exponentially, and that constant number would probably be a positive here. All right, now in a later lesson, we're going to show that this is a good model for this data we've been looking at. All right, now it says use the graph of this model to estimate future levels of carbon dioxide that will double and triple, over the pre-industrial level of 280 parts per million. Now look at that E exponent there. So that's kind of scary here. So here's the K number. Notice it's positive. All right. And then we're going to go ahead from 1990 up T and see what's going to happen here. So the graph shows that it's very close to the data points that we were looking at here. So notice here that for x equals t, y equals 353e to that gargantuan power. And then we'll kind of look at this again here. Now, if we want to look at how long it's going to take to double from 280, we'll say y is 2 times 280 or 560 here. So here is the line y equals 560 on the graphing calculator, all right? That's a horizontal line there. And notice the point at which it intersects our curve is going to be where? It looks like the intersection is going to happen in here. So it says for x equals t, and they've got this formula here. It looks like the point of intersection, time to double, would be the year, it looks like 2065 or 2066 in there. And your calculator will actually do that for you. Now, again, I'm not going to give you one on the test or anything like this, but you may have word problems in your homework that give you some kind of modeling growth or decay, where you'll get some times, and you can input those in your calculator as we looked at in the last video. And time to triple here, 3 times 280 would be 840. So this line here, as you kind of went up the scale here on our calculator and intersected, it looks like it's going to intersect that line at this point right here. So that looks like the year about 2132. All right, so it says the graph of the function intersects horizontal lines at approximately 2065.8 and 2132.5. So according to this model, carbon dioxide levels will double by 2065. Actually, looking up here, I think that's closer to 2066. What do y'all think? And triple by 2132. Maybe it's about halfway through the year on 2132 here. But again, very important, the concepts here. I mean, with global warming and how things are working, how that exponential model follows that too, growth and decay. And you'll find a lot of other problems deal with radioactivity, population growth, and so forth as you do the homework. So these exponential models really do apply in our daily lives. And that's what we want you to see as you learn this math. It's not just always solving an X or doing this. It's actually applying and using it in the real world. All right, so Professor Bob Young signing off.